In this example, we're asked to find the domain of this function, p of x equals the square root of the quotient 15 over x minus 1. So what I want to do is show how you can also access some things within the e-text, kind of as a little bit of a side note, but that also helps us with this particular problem. So let me bring up that e-text. So if you go inside my math lab, you'll see a menu option for the e-text. Right now I'm on page 51. This is within section 1.1. And scrolling down towards the bottom of that page is where we first see this particular objective on finding the domain of a function defined by an equation. You are given an example. On the next page, you're also given a solution. But a little bit further down, this is summarized in this blue text box, where it says finding the domain of a function defined by an equation. You first start with the domain as the set of all real numbers. So we start with that assumption. Then we look to see, does the equation have a denominator, specifically the independent variable within that denominator? And if so, we need to exclude any numbers that give a 0 in the denominator. So we'll look for those things. And then last, if the equation has a radical of even index, think square root, fourth root, sixth root, so on and so forth, we'll exclude any numbers that cause the expression inside the radical, that's called the radicand by the way, to be negative. So in other words, we're looking at solving this inequality where the radicand is greater than or equal to 0. So that's where I got this little blue text box, and just wanted to show you where you can also access that within your e-text. So here we'll follow these instructions about finding the domain given an equation. We start by assuming that the domain is the set of all real numbers, but moving on, we look to see, does this equation have some denominator, specifically where the input variable, x, is in the denominator? If so, we want to set the denominator equal to 0 and say, this cannot be 0. So we're really solving this inequality statement. To do so, we add 1 to both sides and we get that x cannot equal 1. So at this point, we now know that the domain is all real numbers where x does not equal 1. So next we're going to look at this last exception. The last exception is if your equation has some type of square root, fourth root, anything even root. And what we would want to do is set the radicand greater than or equal to 0. And this is because we cannot take even roots of negative numbers and get a real number answer. If you think back, the square root of -4 gives you a non-real answer. So I'm going to do a little bit to this function to begin with, though, because it is like a fraction underneath a radical. I can separate those two using properties of square roots. And the square root of 15 is not very meaningful in this process, just to be honest. What's the most meaningful is this part here, the square root of x minus 1. We've already addressed how it's in the denominator. What we now want to address is we want to set that radicand greater than or equal to 0. So that's what I have written here, is that radicand, the expression under the radical, is greater than or equal to 0. We would add 1 to both sides, getting that x must be greater than or equal to 1. Together, what we get is that x must be greater than 1. And if you're wondering why, it's because we can't have x equal to 1. If x equals 1, we're dividing by 0, and that can't happen. So I don't want to include the 1. So altogether, the restrictions say that the domain is such that x is greater than 1. From there, you are asked to write this in interval notation. And so the interval form of this solution would be 1 to infinity, not including the 1, and we never include infinity, so both of those get a parentheses. And that would be the official answer that we have here inside my math lab. Just really quick, if we want to confirm this, we can express, or we can type in this equation inside Desmos or a calculator, and we could see that the graph confirms that the graph only exists where the x values are 1 or greater than 1. I'm sorry, not 1, but greater than 1. So that's what I've done over here. I hopped over to Desmos, I typed in this function, and I can see graphically it kind of looks like this graph exists where x is 1, here's 1 on my x-axis, or greater, but not ever equaling 1, because it looks to be like this x value is going to get closer and closer to 1, but not actually become 1. And then these x values get greater and greater, just focusing on the x values only of that point. The x values get greater as I continue off to the right side of that graph. Of course, if you are looking at this graphically, you do want to zoom in, zoom out, just to confirm that there's not some other branch on this graph. The graph is just a check to confirm what we did algebraically.